Welcome to PhilSci-Hub Research University, your ultimate guide on your next research project.
We will lay down the best practices in research ideation, literature review, experimental design, and data analysis to guide you as you carry out your research project. Learn from the PhilSci-Hub team of research scientists and some invited subject matter experts. PhilSci-Hub Research University will be your personal coach through every stage of your research project, from ideation to final assessment.
And the best part? It's absolutely free.
Visit us at philscihub.com and be part of this learning journey.
Let's learn and succeed together here at PhilSci-Hub Research University. Welcome to PhilSci-Hub Research University, your ultimate guide on your next research project.
We will lay down the best practices in research ideation, literature review, experimental design, and data analysis to guide you as you carry out your research project. Learn from the PhilSci-Hub team of research scientists and some invited subject matter experts. PhilSci-Hub Research University will be your personal coach through every stage of your research project, from ideation to final assessment.
And the best part? It's absolutely free.
Visit us at philscihub.com and be part of this learning journey.
Let's learn and succeed together here at PhilSci-Hub Research University.
Magandang umaga po sa ating lahat. Welcome to the Filipino Science Hub. Thank you for your continued support to this online platform. To our new participants, thank you for checking us out today, and we would like to officially welcome you to the PhilSci-Hub family. So bago po tayo magsimula, I would like to share some house rules in order to facilitate a smooth session for everyone. For our Zoom participants, we would appreciate it if you could turn your audio and video cameras off during the webinar. If you have questions or comments, feel free to type them on our Zoom chat box or YouTube live comments, and we will try to accommodate as much questions and comments as possible. After the talk, we will have a 30-minute Q&A where the Zoom participants will have the opportunity to ask their questions live. We would also like to request for everyone to not record the webinar. The full video of the session will be posted on our official YouTube channel. For those who would like to receive a certificate of participation, a Google form link will be posted on our Zoom chat box, YouTube live comments, and YouTube video description towards the end of the webinar. Please make sure that you enter the correct information, especially your email address, to ensure receipt of the certificate. Also, for you to obtain the certificate, you will need to subscribe to our YouTube channel as well as follow our page on Facebook. Please note that we receive hundreds of requests and it takes around 7 days or so to process all the certificates. If you do not receive your certificate after a week, please feel free to send us a message on Facebook or email us at philscihub@gmail.com. So again, welcome po sa PhilSci-Hub. Welcome to all our Zoom participants and our YouTube live viewers. For those who are new and may not be familiar with who we are and what we do, allow me to share our mission and vision in the next few minutes. Filipino Science Hub is an online platform founded by our CEO, Filipino scientist Dr. Jeffrey Camacho Bunkin, back in 2012. Currently, we are a registered nonprofit organization based in Houston, Texas, United States. Our mission is to promote STEM education and the culture of research among students and teachers in the Philippines and abroad. Our current global leadership team is comprised of volunteer Filipino scientists and seasoned STEM educators from different parts of the world. Our vision is to see a technology and innovation-driven Philippines, and we believe that this can be achieved by creating a new generation of well-rounded Filipino STEM enthusiasts. This vision is being carried out via our two major programs, the PhilSci Hub Ed program and PhilSci Hub Research University. Through PhilSci Hub Ed, we are able to empower and support our teachers when it comes to strengthening STEM fundamentals education. We believe that this is important because the more equipped our STEM educators are, the more they can inspire our students to pursue a career in science, technology, engineering, and mathematics. Through this program, we have been able to serve our teachers by creating STEM teaching modules as well as conducting teachers training webinars, all of which are accessible on our website for free. So we have also been able to collaborate with major educational organizations that have the same goals and advocacies as Filipino Science Hub. Through these partnerships, we have been able to further expand our reach and help more students and teachers, especially during the time of pandemic. So together, everybody achieves more. The other major program that drives our vision forward is PhilSci Hub Research University. We believe that in order to strengthen a STEM culture, students also need to be able to learn how to conduct a scientific research. As we know, many scientific and technological breakthroughs happen through research, and we would like to equip our younger generation by providing them proper scientific research training. So ika nga po, start them young. Here at PhilSci Hub Research University, we provide free courses on fundamentals of scientific research, such as research ideation, literature review, how to write a research proposal, how to communicate your research work to the scientific community, among other courses. Through this program, we are also able to bring practicing scientists closer to the STEM educational sector. So because of this closer contact, our students become more aware of the possible STEM career paths available for them and how these careers contribute to the advancement of the society around them. So up to date, we have been able to reach over 70,000 students and teachers all over the world, and we know that this will continue to grow in the years to come. And this is why we are all very excited on what is in store here at PhilSci Hub. Our official website is www.philscihub.com. This is where you can access all our materials such as webinars, tutorials, modules, virtual lab, and special features. We are also present in several social media platforms such as Facebook, LinkedIn, YouTube, and TikTok. So follow us wherever you're most active on to get updated with our web events. So again, thank you for being with us this morning. And to officially start our webinar, I would like to turn the virtual floor over to our host for today.
Alright, magandang araw po sa inyong lahat. Magandang umaga po sa Pilipinas. Magandang gabi po dito sa Amerika. Ako po si Jeffrey Bunkin and I'm the founder of Filipino Science Hub. So before we begin, I would like to welcome you all po sa session ngayon and muli magpapasalamat po kami sa pagsama po ninyo uli sa amin sa isang Sabado. So would you believe that since we started rolling out webinars po in 2020, a total of about a year and a half actually, we have already conducted about 60 web events. I think this is the 61st, if I'm correct. And so far we have already trained about 30,000 live participants. So halos na puno na po natin ang Araneta ng 2 beses. And so ito pong araw na ito ay special dahil ito po ang at final offering ng Filipino Science Hub for this year. So after po nito, magbabakasyon muna po tayo ng 2 weekends and then we'll be back sometime in January. Okay, so ngayong araw po na ito, we are actually graced by a Filipino scientist based in the United States of America. And specifically, she will talk about per and polyfluoroalkyl substances. So this is actually medyo mas chemistry heavy. And so for today, we have Dr. Mary Grace Garjan. So to formally introduce our speaker, may we call on PhilSci Hub's one of PhilSci Hub's like leadership team members, Dr. Dindy Voice. And nga pala, announcement nga pala po, before ko tawagan si Dr. Dindy. So tune in po kasi after the Q&A, magkakaroon po tayo ng raffle promo. So ngayon po mamimigay po kami ng isang ring light at ng isang organic chemistry model kit. So watch out for the instruction po sa dulo para po malaman niyo on how you can participate dun sa ating raffle promo. All right. So Dr. Dindy, are you ready?
All right, Jeffrey. Thank you, Dr. Jeff. I reclaimed my hosting privileges, just so you know. So good morning po sa lahat. And like what Dr. Jeff said, we are very excited about tonight, or this morning rather, dahil this is our last webinar for the year. And it's my honor to introduce our special webinar speaker for this morning, Dr. Mary Grace Garjan. She's a very good friend of mine. So siya po ay nagtapos ng Bachelor of Science in Chemistry from the University of the Philippines in Los Baños, Laguna. And after that, she got a master's, European Master in Quality in Analytical Laboratories in Gdańsk University of Technology in Poland. And she also got another master's degree in Quality in Analytical Chemistry from Universitat in Barcelona, so that's in Spain. And then, of course, she got her PhD in Analytical and Environmental Chemistry from University of Buffalo here in New York, United States. So in terms of professional background naman po, she was an assistant professor at University of the Philippines in Los Baños from 2011 to 2013. And then after that, she worked as a chemistry lab supervisor in Nestle Philippines. She was there for 3 years. And then she became a research assistant in chemistry department at University of Buffalo in AGA Lab, again, also in New York. And currently, she works as a senior scientist at Eurofins Agroscience Services in Maryland, United States. So without further ado po, I give the floor over to, or virtual floor over to Grace. So Dr. Grace, you may take it away now.
Okay, thank you, Dindy, for a very nice introduction. So I should share my screen, right? I'm gonna share.
Yes, Grace.
Wait. Okay, can you see it?
Yes, we can.
Okay. Okay, so magandang umaga po sa inyong lahat na nasa Pilipinas, and of course, good evening to those who are in the US right now. So thank you, Dindy, for a very nice introduction. So for this presentation, I will be presenting what's in your water, and I'll be basically introducing you to this very controversial group of compounds called per and polyfluoroalkyl substances, or PFAS. So earlier, in-introduce na ako ni Dindy, but then I want to tell you a story of my career path. So I'm basically from Bicol region. So pinanganak po ako sa Gubat, Sorsogon. So I was born there and then stayed there until high school. And then nung high school ako, favorite subject ko talaga is chemistry because I really love my teacher. So she basically inspired me to do a Bachelor of Science in Chemistry sa college. So when I was applying for degree for college, so I basically applied only to UPLB and then to BU, which is Bicol University. And then first choice ko talaga is always a Bachelor of Science in Chemistry. And I was lucky enough to be admitted at UPLB. So I basically earned my degree last 2000 at the University of the Philippines, Los Baños. And then after college, I worked as an analytical chemist at the Johnson Nutrition. This is formerly a part of Bristol Myers Squibb, Philippines. So if you are familiar with Lactum, with Tempra, so basically yun yung main products namin before. So here as an analytical chemist, the work is mainly, basically the role is mainly on the quality control system. So basically in the lab, so ang trabaho ko nun is to test really if kung ano man yung nilalagay namin sa label is true. And then when I was working in the industry, gusto ko maging supervisor kaagad. Lab supervisor, but I think I was too young and it's too early. And then I have a friend who was working before at British Embassy in Manila, and she told me, you know what? Do you want to go to Europe? I said, sure, why not? And then let's attend this European higher education fair. So there was a fair way back. I can't remember the year anymore, but we attended there, and then we're so impressed by these different universities that promoted their programs, and we're lucky to be accepted in the programs that we applied for. And so after that, I went to Europe. So basically, I earned European Masters in Quality Analytical Laboratories. So this is a 2-year program. And then the first year, we took all the theoretical courses in Gdansk. And then I moved to University of Barcelona for the thesis. And during my master's degree, I was really, really happy that time because I can also travel. I love traveling a lot. And then but then afterwards, I got homesick and I said, I want to go home. And then after master's, I went back to the Philippines. I work as assistant professor at UPLB. So for about 2.5 years, I think. And then basically I was teaching analytical chemistry courses. So both lab and lecturer, and then also as a Gen Chem. And then after UPLB, finally nakuha ko na yung dream role ko before, which is to become a chem lab supervisor. So I was hired as a chemistry lab supervisor at NQAC. So NQAC stands for Nestle Quality Assurance Center. So basically, we're overseeing quality assurance for all manufacturing facilities for Nestle Philippines. But then that time I was still kind of young, but then I managed people. So I have probably maximum of 10 chemists reporting to me. And of course, since we are kind of implementing methods, we are validating methods. But then we are more of following what the Nestle Research Center, which is in Switzerland, kung ano na yung na-develop nila. So ini-implement na lang namin sa Pilipinas. So it was kind of hard because, you have the time different. So when I need like technical expertise, I have to communicate with them. But then my people needs like fast answer to all their questions. So I realized that time, you know what, gusto kong maging PhD so that maging expert din ako. So because like all the people in NRC have PhD degrees. So it's like, oh, I want to be one of them. And so I decided, okay, I'll do PhD. But then I don't know where to go. So I realized, I've been to Europe. Maybe I will try US this time. So because I really love traveling. So for me, if I study, I can also travel at the same time. So applying for a degree in the US. So first, I don't know what school to apply for. But then I realized I know Dr. Diana Aga. She is like a full professor at University of Buffalo, which in turn, she became my advisor. I met her in one of the symposium when I was still an assistant professor at UPLB, and then I sent her an email. I asked her, "Are you looking for like a PhD student?" And she said, "Yes, I'm currently looking for now." So, and then basically communication. I asked her, "What are the things I need to do? What are the requirements?" And then I went apply. And so to cut the story short, I was admitted as a student at the University of Buffalo. So basically for the degree of PhD in Analytical and Environmental Chemistry. So as you can see, my core is really Analytical Chemistry. And then when I was working before grad school, so it's more of like a quality control application in a manufacturing labs. And then when I did a grad school, so the application shifted. So basically from the core is still analytical chemistry, but the research is more on environmental chemistry. So I finished my degree last year. And then after that, I was accepted as a senior scientist at Eurofins Agri-Science Services. So Eurofins is a CRO. So we're basically doing toxicity studies for like private companies. And then we're for new chemicals that will be introduced in the market. So my role is more of an study director. So I like work on like method development, I didn't implement it. And then after that, once the method is developed, so we'll do the toxicity studies for our clients. So that's all. Now, sorry, I just want to try to move things around so that I can see the. Okay, so for my presentation outline, so basically, I will be starting with the introduction of what is this group of compounds, and then after that, I will discuss 3 research that I did when I was still in grad school. So the first one is about prevalence of PFAS in drinking and source water, which we collected in the Philippines and Thailand. And then followed by another research about resolving unknown isomers of PFAS in environmental samples. And then last is capture of PFAS in water using metal organic polyhedra. So probably most of you knows already what are PFAS, especially if you have watched this film. So in Netflix, there is a documentary entitled "The Devil That We Know," and then and also in 2019 there was a movie about the dark water. So both of these are basically discussing PFAS, and because of the environmental effects of PFAS, it gained a lot of press releases in both scientific communities as well as in local press. So as you can see here, it's the Gen X problem in North Carolina is like a cover article in Chemical and Engineering News. And you can see like here in New York State, some news about having strict PFAS water drinking limits and many others. So ano nga ba yung PFAS? So basically, PFAS, tinatawag din siyang forever chemicals. So these are called for forever chemicals due to the very stable, because they are very stable due to strong fluorine and carbon bonds. So as you can see, meron ako ditong 5 structures ng PFAS. So you have here, basically lahat sila fluorinated, and then you have here the head group. So the perfluoroalkyl substances are those in which all hydrogen atoms attached to all carbon have been replaced by fluorine atoms. So example, you have here structures 1, 2, 3. So basically you have here the head group. So wag natin i-count yung head group, and then you have here the tail. So as you can see from carbon here up to the end, up to the terminal carbon, totally fluorinated sila. On the other hand, yung poly naman, all hydrogen atom attached to at least 1 carbon have been replaced by fluorine atoms. So in this example, I have structures 4 and 5. So structure 4, meron kayong 2 carbon na hindi pa fluorinated. So this is still CH2, and then here you have here also not fluorinated. So collectively, tinatawag siyang PFAS. So kina-classify din ang PFAS according to chain length. So, but this classification is basically used for perfluoroalkyl carboxylic acid. So that means yung head group niya ay COOH. So among sa 5 example ko, meron lang akong isang carboxylic acid dito. So long chain, pag yung carbon chain mo ay more than 7, and then short chain yung below 7. So another classification is perfluoroalkyl sulfonic acid. So that means sulfonate yung head group mo. So basically from structure 2 to 5. So you have your SO3H hanggang dito. So long chain naman are those na about at least 6 ang chain mo. So another classification of PFAS, so legacy and emerging. So the most well-studied PFAS are perfluorooctane sulfonic acid or PFOS and perfluorooctanoic acid or PFOA. So these are the structures. So basically, again, this is fully fluorinated. So lahat yan attached na to fluorine, and then you have here the sulfonate, and then you have here the carboxylate. Several studies have shown that these are known to cause multiple toxicities to both animals and humans, such as endocrine disruption, reduced fertility, and then a link to also several cancers. So because of these long legacy PFAS, such as PFOS and PFOA, were phased out starting year 2000. And right now it's regulated in several countries. In the US, the EPA, or Environmental Protection Group, issued a drinking water health advisory of 70 nanogram per liter in drinking water. But right now, they just released an EPA PFAS strategic roadmap. So in this project, they're not just looking for PFAS in drinking water. It's basically in the environment as a whole, and then they're looking into what are the possible replacement of PFAS, what are the possible remediation. So because these are phased out, so industries replace this with short chain homologs or less fluorinated compounds referred to as emerging PFAS. So why PFAS are used in several industries? So number one, they're very, very stable because of the strong fluorine and carbon bond. Second one is that meron silang water repellent property, because this is because of the change of carbon fluorine. And then they also have oil and grease repellent property, mainly because of the head group that usually contains like oxygen, sulfur, and nitrogen, which make it like polar. So because of these properties, so PFAS are used extensively. So as in this table, makikita nyo yung iba't ibang application ng PFAS. So it's used from automotive to basically textile, leather, and apparel. Right now, it's still used in firefighting foam. So basically the firefighting foams probably contain 90% PFAS. And then for us, so these are also used in consumer products that we basically use every day, such as in food packaging. So the microwave popcorn bags, sandwich wrappers, pizza boxes, and many others. It's also used in outdoor gear, especially those like water repellent clothing. So sa mga nagluluto po, ginagamit ko to as coating for those non-stick cookware. So basically that's Teflon. And then it's also used in furnitures and some other consumer products that we use every day, such as in makeup, in dental floss, and many others. So because of this extensive use, so PFAS has become an ubiquitous environmental contaminants. Several studies have shown presence of PFAS in different water systems. So you have lakes, river, marine water, and even in rainwater. And of course, in aquatic organism or so like from small to like dolphins, they are already detected. And because PFAS are also soluble in water, so they have very long transport range. So even though, like example, you have a manufacturing facility in the US, time will tell that soon enough the contamination will go somewhere else because it can be transported through water. So, and then it can be accumulated also like in the soil. So it is found in sewage sludge, garden soil, and even in plants because the plants will uptake it. And then these are very stable compounds. So even the most sophisticated water treatment system were not able to really remove PFAS in drinking water. So they are still detected in tap and even in bottled water. And of course in humans, so they are detected in blood, in breast milk, and other important tissues such as liver, brain, lung, bone, and kidney. So this figure shows you PFAS exposure for humans. So basically one is use of consumer products that contain PFAS. So consumption of like fish or drinking water that are contaminated. And for those that are working in a manufacturing facility, so they have like occupational exposure. And for those also living near these manufacturing facilities because of emission. So they are basically highly exposed. And then this figure shows you the different health issues that are linked to PFAS. So for unborn child, so PFAS are known to cause delayed mammary gland development, reduced response to vaccines, you have lower birth weight, and many others. And for both gender, so PFAS are linked to thyroid disease, cholesterol levels, breast cancer for women, and then liver damage and many other cancer problems. So as you can see, PFAS research in PFAS is really, really necessary. So here I'm just want to show you like the PFAS contamination that is from the EWG or the Environmental Working Group. So you can go to their website, and then this map shows you the contamination in the US. So it doesn't tell you the levels, but it just tells you where they are. So as the purple ones are the military sites, and then the blue ones are the drinking water where they are detected, and then the orange or other known signs. Usually these are like previous manufacturing facilities. So if you go to their website, all the dots are linked to like publications, and so you can read the publication, and then this will tell you what are the PFAS that are detected in that particular area and then the concentration level. And then the EWG is actually really actively doing this. So they even like email me like any contribution from your country that maybe we can add to this map. So as I mentioned earlier, PFAS is a global problem because of the long transport range of these compounds. So however, in high-income countries, they have a lot of research, especially like here in the US, in Europe, and then Japan, Australia. And they already phase out legacy PFAS, and they're really doing a lot on having a strict regulation for this group of compounds. And then actually in the EU, they started regulating PFAS as a class, and I think in the US, EPA is also doing the same thing. However, in Southeast Asian countries, they have very limited to actually non-PFAS research. So for this first work, I did basically range finding of PFAS levels in the Philippines and Thailand. So why I chose Philippines and Thailand? So basically, galing ako sa Pilipinas, so I want to know. And then in Thailand, we have also active collaboration there. So we have a collaboration with Dr. Prapa Arnox. She is a professor at Ramkhamhaeng University in Bangkok, and Dr. Rajana Burakham, also a professor at Konkan, Thailand. And sa Philippines, I'm very lucky na meron akong friends na may-ari ng lab. So I collaborated with them. I asked them na pwede ba akong mag-lab sa inyo while during the sample collection. So, and they happily agreed. So for the sample collection, these are the sampling sites. So in Thailand, so basically we collected samples from Ubul Ratana Dam and then Lampao Dam. So these are in Konkan. And then we collected also samples along Chao Phraya River. So Chao Phraya River is the longest river that passes through Bangkok. Then sa Pilipinas, nag-sample ako sa Laguna Lake. So 2 sampling sites sa Laguna Lake. So basically here in Sucat, Parañaque, which is highly urbanized. And then the other one is in Victoria, Laguna. So this is more of agricultural area. So bakit ko to pinili na sampling site? Because one, these are all drinking water source. And then secondly, these are used in aquaculture, and then of course marami nangingisda sa Laguna Lake, and then of course used also for irrigation, recreation, and ecotourism. Besides this source water, I also tested with several bottled water from both countries. And then in Thailand, nag-collect na ako ng samples from vending machines. So a lot of people, especially in Bangkok, rely on drinking water from vending machines. So papakita ko lang sa inyo mga pictures during sample collection. These are like the fun part. So ito yung Chao Phraya River. So meron kaming 3 sites dyan na kumuha ng sample. So the first one was taken here. So this is in Nuntabure. This is about 2 hours drive from Bangkok, from central Bangkok. And here, hindi pa siya masyadong highly urbanized na area. And then, of course, we collected sample in Bangkok. And then here, like about an hour south of Bangkok. So this area naman, palibot siya ng maraming manufacturing facilities. And then in Konkan, Thailand, we collected samples at 2 like largest dams there. So this is like the top view of Lampao Dam. As you can see, it's surrounded by a lot of freshwater fish farms. So the quality of water here should be really be monitored. and then another sampling site from Ubulratana Dam. So these people are like students of Dr. Rojana. They helped me collect the samples, and this is me. And for Laguna Lake, so again, we collected samples here in Sucat, near Sucat Parañaque, and then another one is here in Victoria, Laguna. So this is Kevin, ang employee doon sa lab ni Val, and then this is us during sample collection. So the problem with collecting samples from the Philippines, especially its water samples, I cannot bring back my samples to the US. They will not allow me to come back to US with like how many liters of samples. So I have to do sample preparation to in both Thailand and the Philippines. So in the Philippines, I work at Buong Galing Laboratory. So basically, I collected 1 liter sample, we adjust the pH, and then you filter it, and then you add it with internal standards. So this internal standard, or we call surrogate, will basically help us deal with possible degradation, because diba, from Philippines, dadalhin ko pa siya dito sa US. So pwedeng mag-degrade yung compound, so along that time. And then I use solid phase extraction to basically collect my analyte. So nung umuwi ako ng Pilipinas, dala ko tong mga manifold na to. So dinala ko yung manifold ng SPE. I brought also like cartridges and many other things. And then, so basically I have to load the sample, and then the analyte should stick to these cartridges. And then after that, I dry the cartridge and then store it frozen. And then I brought the cartridge back with me to the US. So instead of bringing like 1 liter sample for each sampling site. So pagbalik ko dito, dala ko ulit yung mga manifold na yan, and then the cartridge na meron ng sample. And then here, I have to elute my analyte from the cartridge. So basically, I eluted it with ammonium hydroxide and then reconstitute. And then I add internal standard to account again for the possible losses. And then I analyze it using LCMS, using basically Orbitrap. So this is the method that I use for analysis. So previous to my trip to collect samples, dinevelop ko na tong method. It took me probably a month to develop this. So basically, I need to separate my compounds using chromatography and use high resolution mass spectrometry. So hindi ko na to masyado i-discuss. It's very, very technical. But then I'll discuss to you later yung results na lang. So here, basically, I have LCMS, and then this is my mobile phase, and then you have here the column, and then the parameters for my mass spectroscopy. And then this one, I'm just showing you like the chromatography that has been optimized. So these are the PFAS that we have available reference standards. So group A, so basically, ito yung mga carboxylic acid. So PFBA means perfluorobutanoic PFBA, so perfluorobutanoic acid. So butane, that means this is C4. And then I have standards until FIFODA. FIFODA is octane decanoic, so basically C18. And then group B, you have C3 sulfonate, and then have until 10 sulfonate, and group C are like other PFAS. And then this is your linear range in terms of a nanogram per liter. So I'm gonna introduce you a little background of how we analyze organic contaminants. So basically, as analytical chemists, so we analyze, well, basically we analyze low volatile CEC. CEC stands for contaminants of emerging concern such as PFAS. So we use liquid chromatography tandem to mass spec for hindi masyadong volatile na compounds. And then gas chromatography for volatile compounds. And then using high resolution mass spectrometry, which gives you a very accurate mass, you have like 3 ways of doing analysis. So basically the sample preparation is the same, but then you have like 3 approaches. So first approach is target analysis. So sa target analysis, you are basically, you have the standards. So alam mo ang hinahanap mo sa sample mo. So you're comparing apples to apples. So you run standards together with your samples, and then after that, you want to identify if that standard is present in your sample. And then since you have the peak areas of the standard, then you can do a quantification or makikita mo yung concentration. And then the other approach is suspect screening analysis. So dito naman, meron ka lang suspect list. So may suspect ka na, meron ba to? Yung sample ko ba merong PFAS or wala? So here it's more of like a software processing after the instrumentation. So because dito gumagamit ka ng suspect list. So yung list mo, of course, are the masses of your possible compounds. And then sa non-target analysis naman, so dito talaga naghahanap ka ng unknown. So wala kang idea except that yung raw data mo lang. And then you compare your raw data to a lot of like several databases that are available. So in target analysis, so you can easily do it as long as you have standards. So, and then your accuracy here is always 100% because you compare it to a standard, right? But in suspect screening and non-target, accuracy is usually defined by Szymanski classification. So level 1, so that means confirmed structure. So after nung suspect screening, so meron ka ng idea kung ano yung compound mo, and then you go back and then search, oh, is this compound available in the market? Can I buy it? So basically, babalikan mo yung data mo. So pag nabili mo na yung standard, then you can confirm it. So that's level 1. So for target analysis, it's always level 1, right? Because you have a standard. And then level 2, you have the probable structure. So basically, meron ka lang idea because of the mass of the compound, and then some other comparison based on literature. And then as you go along, so the level decrease. Hanggang level 5, so yung accuracy ng identification mo, bumaba pa. So let's start first with target analysis. So ito yung results ng aming research. So these are for those samples collected in the Philippines, and then this one is Thailand. So basically, ito yung mga na-identify namin na PFAS. So total number of PFAS detected. So dito naman yung drinking water and source water. So drinking water, we were able to detect 11 PFAS. And then sa source water, 15. Tapos ito naman yung range niya. So sa drinking water, 9.08 to 11 nanogram per liter. And then 50 naman to 35 sa source water. So which is still lower dun sa EPA health, drinking water health advisory na 70 nanogram per liter. So in Thailand, so you have here the drinking water. We were able to identify 12 PFAS from the drinking water, and then sa source water naman 12 din. But as you can see, mas mataas talaga ang level sa source water kasi yun yung parang raw water. So at least yung sa drinking water, somehow may process na yan na dinaanan. So long chain PFAS are usually removed along those drinking water treatments. So, so here, this figure shows you yung detection namin this is from the Philippines, so basically Laguna Lake. And then this is from Thailand. As you can see, these are the different PFAS that we detected. And then the total concentration is about 65, yung pinakamataas na, which na from Chao Phraya River sample. So as you can see sa Philippines muna, sa Laguna Lake. So ito yung from Victoria, Laguna. Ito naman yung from Sucat, Parañaque. So we detected more sa Sucat, Parañaque, which can be, and then yung level niya mas mataas, which can be explained kasi di ba medyo urban area siya compared dito. Same trend ang na-observe namin from Thailand samples. So here is along the Chao Phraya River collection site. So makikita nyo, so from north, medyo agriculture area pa siya. So mas kunti pa yung detection, and then the level is also lower. And then this is from Bangkok, central Bangkok, and then this is like southern. So as you can see, since nata-transport yung contaminants mo, so you expect high levels really at this point. And these are the ones that are identified and quantified from those dams. Makikita nyo, very high level ang PFHPE. This is C7 sa Thailand. And then when we were like doing the research, it can be a link to like a lot of clothing business or clothing industries sa Thailand kasi ginagamit siya doon. So this one naman shows you results sa drinking water. So we tried to compare results ng drinking water dun sa mga available na mga published results from different countries. So this is example, this one is from Canada, published in 2018. This is in US, Brazil. So this is the one that we detected during this study. So this is from the Philippines and Thailand and so many other countries. So ito shows you all drinking water types. So pwedeng tap water siya, pwedeng bottled water. And then I also tried to just summarize yung sa bottled water because we think yung bottled water dapat wala tayong makitang PFAS dun. But unfortunately, in several countries, marami na talaga siyang na-detect. So this is from Canada, Brazil, and this is from this study. So Philippines and Thailand, and then some other countries. However, you can see the levels in bottled water is still lower compared to all types. So here makita yung axis from 0 to 350 nanogram per liter. Here it's from 0 to 80 nanogram per liter, but still it's already present in commercial bottled water. So after target analysis, we wanna expand our research to look at what other PFAS could be present in my water. Kasi as of now, there are probably around 6,000 PFAS already identified in the environment. But however, yung available lang na standard siguro is for about 100 PFAS. So there's like so many other things that are not identified and there's no available standards. So for this one, we have to use the other approach. Di ba kanina target analysis, meron tayong standards. This one, wala tayong available na standards. So I'm gonna use a suspect screening approach here. So as I mentioned earlier, yung present ko na results is just using target analysis. And then for this one, I'm gonna use a suspect screening analysis. So sa suspect screening na ginawa ko, so I downloaded the PFAS list from EPA. So when I was doing this research, this list contains only probably about 5,000. But I just check it now. The list is really growing so fast because it's already 12,000 PFAS. So I downloaded it before and then I use a software. So this is basically part of the instrument. So and then I set like the error that is acceptable. And then after that, I do like another software and then manual interrogation, because you really have to identify like what are these fragments mean from the mass spec. So using this suspect screening process, we were able to identify 1, 2, 3, 4, 5, basically 6 more PFAS that are not identified using target analysis. So, and then I mentioned you earlier yung confidence level, how we define it. So this one, TFMS and PFPRA, naging level 1 siya kasi after namin ma-identify using suspect screening, we were able to buy a standard. So basically, binili ka namin yung data, and yes, it was confirmed that these are the identity of those PFAS. And then for others, we have here level 2A. So this is still probable structure, and then level 3. So because the main issue for research now is that we don't have enough available standards that we can buy or even synthesize. So we have to do some other ways to make sure na yung mga probable structure ay at least, medyo accurate. So this time, I will be introducing you the next project, which we collaborated with a theoretical chemist. So for the Orbitrap LCMS, so basically, meron akong dalawang information na makukuha. One is the MS2 fragmentation. So basically, you have the mass spec, and then you bombard it with energy, and then that compound will fragment, and then you will get the fragmentation pattern. And then sa liquid chromatography, you have basically the chromatography. So you have retention time of your compound, or here I use the retention factor. So these are the experimental data na makukuha ko from my analysis. And then we collaborated with Dr. Scott Simpson. He is a theoretical chemist. So basically, they are more on like software analysis. So they can calculate the log KOW. KOW stands for octanol water partition coefficient. So it can be used as the measure of hydrophobicity of your compound sa analytical column. And then they can also measure the mean polarizability. So we basically make a model in such a way na mapipredict namin accurately yung PFAS. So we created a model using the standards that we have. So I analyzed that using the optimized methods. So I have the fragmentation pattern, and then I have the retention factor. And he calculated the log KOW and then the polarizability for each standard. And then we combine our data, and we were able to make a model in such a way that we can predict the retention time of an unknown PFAS. So before I discuss you our research, magdi-discuss lang ako how chromatography works, because I think it's important, especially for like high school students na nasa audience. So it's a very i-discuss ko lang siya in a very simple way. So basically, you have the mobile phase here. So it flows through your system, and then you have your sample that contains a lot of analytes, or for this case, possible several PFAS. And then you introduce it to the system, and you have the analytical column. So depending on property of your analyte in your sample, meron silang different interaction with the column. So for those analytes na mag-interact sa column, so tatagal siya sa column. Pero yung walang interaction, mag-i-elute siya kaagad. So example, this compound, mag-i-elute siya kaagad kasi hindi mo siya mag-interact. But this one will interact there for a long time, so mag-i-elute siya taas. So this compound will be this one, and then this one will be this one, and then this next one. So basically, that's how it works. And then as we will only get this information. So for PFAS, di ba, same lang yung usually per group of PFAS, same lang kanilang head group, pero nagbabago yung kanyang chain length. So example here, you have C4. So you have like C4. So 3 na fully fluorinated, and then you have your carboxylic acid as a head group. So this is C4. Example, this is your C4, and then this is your C6. So if my unknown dilute somewhere here, then I could probably tell, oh, it's probably a C5. Or if this is PFOA, that's C8, so the C7 will probably dilute around here, right? So that's it. And then sulfonates is the same. So you have one functional group, and then iba-iba lang yung length mo. So the shortest length will be here, and then the longest will be the last, because it will interact more with your column. Similar trend ang makikita mo for each group. So from there, if we have an unknown and we have like a model, then we can predict where that possible unknown will elute, or from this chromatography, nasaan ba siya. So that's the LC part. The prediction will be done by the theoretical chemist. So they will do like all these calculations. And then, paano naman yung mass spec? So mass spec, so kaya tinawag na mass spec. So ang mini-measure niya ay mass ng compound. So this is a very simple illustration how it works. So example, you have benzamide. So yung kanyang molecular, so if it lose electrons, so yung mass niya, so it becomes M+, the mass is 121. So that's what we call molecular ion. So ito yung 121. And then, you bombard it with energy, and then pwede siyang mag-lose ng NH2. So pag nag-lose siya ng NH2, magiging ito siya. So that gives you the 105. And then, or pwede siyang mag-lose nito. That gives you the mass of 44, which is this one. Or this one could also still lose the, yes, and then gives you the mass of 77. So that's basically the main information that we get from mass spec. So you have the molecular ion, and then you can fragment it so that in such a way, you will know the fragmentation pattern for each group. Okay, now that you know like the fragmentation pattern, so I'll show you like the experimental results that we have for each PFAS group. So let's start with perfluoropentane pentanoic acid. So this is COOH, but perfluoropentane, so that's C5. So this shows you, so ito yung mass spectra at 10 electron volts, this is at 20 electron volts, and this is at 30 electron volts. So ito yung mga na-observe namin. So anong equivalent niyang 262 na yan? So ang 262 is the molecular ion, which is nag-loss siya ng, so M-H. Nag-loss lang siya ng hydrogen. So that's this one. And then the 218 is after neutral loss of carbon dioxide. So first mag-loss siya ng hydrogen and mag-neutral loss. So basically this fragment, that is equivalent to 218. And then the 118 is loss of C2F5. So basically this one, so fragmentation niya is here. So that's one. So as you can see, sa 10 electron volts, makikita niyo pa yung molecular ion. And then as you increase the energy, di nyo na siya makikita. Makikita nyo yung 118 na, yung terminal, this one, C2F5. So that's first example. Now let's move on to like a longer chain. So perfluorooctanoic acid. So this is C8. Tingnan natin kung may pattern sila. So ito yung na-observe natin. So 412, again, this is M-H, nag-lose lang siya ng hydrogen. And then the next mass that we observe is actually same. We're losing carbon dioxide. So after neutral loss of carbon dioxide, and then we also observe 218. So basically you're losing this. So this is 218, this one. And then you have the 168 and then 118. So 168 and then 118. So we analyze probably around 10 octanoic, basically carboxylic acid. And then we basically observe the same trend. So basically, first, you will observe at 10 electron volts yung loss ng hydrogen. And then the second that you will observe is neutral loss of carbon dioxide, and you have the fragmentation until it reaches this terminal fragment. So that's example for carboxylic acid. How about sulfonic acid? So again, this is SO3H. So earlier, my example is perfluoropentane pentanoic acid. So that's still C5. And this one is perfluoropentane sulfonic acid. So same sila except that magkaibang kanilang head group. So from here, iba naman yung fragmentation na na-observe ko. I still observe that M-H, but then we're not observing here like loss of SO3. What we're observed or loss of these CF2 units, what we what we are observing is only 98 and 79, and then the 98 and 79 correspond to FSO3 minus and then SO3 minus. So this is C5. Let's go to the same length as my previous example. So this is C10 pala. So same lang. So for sulfonates, basically, ang makita lang natin is yung M-H, yung molecular ion, and then the presence of these 98 and 79. We will not observe like the sequential loss of CF2, which is observed in carboxylic acids. So that's already two groups. This one is sulfonic acid, so fluorotellumer. Ang difference naman ito, this is a polyfluoroalkyl, so that means meron silang hindi fully fluorinated. So this is CH2 and CH2. What we are observing is kind of different. So here we observe M-H, but then you have observed the 406. 406 is actually loss of HF units. So nagkakaroon siya ng rearrangement. So here and then you have also the 80.96. So that's 6.2, and then this is another length. So same, we observe the M-H and then loss of HF because of, then we observe the 506 and then also the common fragment, which is 80, which corresponds to HSO3 minus. So these are like the new PFAS, Gen X. Gen X is basically a replacement for PFOA. So this is the structure of Gen X. So what they are doing, like the industry, instead of like totally fluorinated, so all carbons, they are putting like here an ether group. So for Gen X, and some other ethers, what we observe is they basically fragment where you have the carbon-oxygen bond. So it's either here or here, and then you observe also the 118, the terminal chain for this one, and then you're also, because the head group here is still carboxylic acid, so you are still observing loss of carbon dioxide. And then these are just some other examples of different groups. So ethos, again, this is an ether, so this is Adona. I think Adona is a replacement for, also for PFOA, I guess. So as you can see, it fragments where you have the carbon oxygens, either here, or then here. So we summarized all this fragmentation pattern, and then we like have, we summarized all this fragments, and then we were able to have this pattern trend. So for each class, we know how it behaves in the mass spectrometry using that specific voltages. So you have here PFCs or carboxylic acid. So basically the common fragment mass that we observe is the terminal C2F5. You have the sulfonates here. We're observing the 98 and 79. So these are other groups. And then you have here the ether perfluorosulfonates. You observe also 98 and 82. And then as I mentioned earlier, the ether for ethers, the fragmentation will occur at the CO band of the ether functional group. And then these are some other examples. So with this trend, we can have an idea what is the probable structure of our unknown based on the mass spec that we obtained experimentally. So now we have the database or the fragmentation pattern from the standards that we analyze. And then we have our collaborator can calculate the retention time of the possible structure of your PFAS. So, and then using that model, we applied it to the new PFAS that were identified in, basically you have here, I have 5 unknowns. So yung unknown number 1 and then unknown number 5, na-identify namin to dun sa kaninang diniscuss ko na paper, which I think we detected it in, probably in Thailand, from waters from Thailand, and then this one as well. And then these 3 unknowns, this is from another collaborator. He's actually working at EPA, and then he just provided as a sample. But they already published this paper, and then they provided this structure. So, and then we analyzed this using our method. So, PFAS has a lot of possible isomers. Kasi example, you have especially the polyfluoroalkyls. Remember the poly, hindi siya totally fluorinated. So yung hydrogen mo, pwede siyang mag-jump in any carbon, right? So that means it's another isomer. So during the analysis, we observed that the sample unknown 3 and unknown 4 have 2 peaks. So this analytical peaks. So this as for unknown 3, same mass, we have here peak 1 and then second peak. So that means it's possible the isomer sila. And then also for unknown 4, we also observed 2 peaks. But for this presentation, I'll just show you how we determine the most probable structure for unknown number 2 and unknown number 4. So let's start with unknown number 2. So experimentally, we ran the sample. This is the mass spectra that we obtained for unknown number 2. So ito yung kanyang observed mass. Ito yung formula. Yung ion assignment, I did it myself. So I have to do like all the math and other things. And then this is the mass error using this ion assignment. So using this mass spectra, the most probable, if we have to guess, it's really a sulfonic acid. Why? Because we observe the 98 and 82, which is common fragment for sulfonates. So based on this information, the most probable structure for this unknown is this one. So because if you fragment this structure here, makukuha mo yung that is equivalent to 184, which is this mass. Now let's combine the mass spec and then the retention time prediction. So the experimental retention time for this is 7.52 minutes. And then using our model, the calculated retention time is 7.84. So using this structure, basically this structure. So the percent error against the experimental is 4.19. However, pwede din naman siyang ganito ang kanyang structure, di ba? So if I move the oxygen here to here, what will be my calculated retention time? So if I move my oxygen dito, what happens is that the calculated retention time is already 8 minutes. So the percent error is even higher. And then if you move it here, the error is 6.13%. And then if you move here, the error is 5.52. So basically, combination of your calculated retention time and then the mass spectra that you obtained experimentally. So ito na talaga yung kanyang most probable structure. So this one. Okay. Next is, let's go to the more complicated one because we observe her 2 peaks is the same mass. So most probably isomer sila. So this is the mass spectra for the first mass, for the first peak. And then this is the mass spectra for the second peak. Again, same sila ng molecular ion, but the fragmentation is different. The main difference is that the mass fragment 246 is not observed in our in the first peak. So these are the assignment. So the 246 mass is only observed in the second peak, the 4B, but the rest are basically the same. So from using the mass spec alone, so this mass to this mass is a loss of HF, and then this mass goes in this mass, so you have CH2. So basically from that information, pwede ka na mag-draw kung anong possible niya na structure, right? And again, we know that it's sulfonate. The head group is sulfonate because we observed the 98 and then the 82. This is the common fragment for sulfonates. So let's start with unknown 4A first. So first possible structure is this one. Why this one? Because the 232 is actually this fragment. So remember, if it's an ether, it will fragment at where you have the carbon and oxygen, right? So it will fragment here or here. But if we fragment it here, this mass, then loss of this mass and then is equivalent to 232. So let's calculate. However, if the hydrogen is here right now, but it's still the same mass, even if the hydrogen is here or this or here or here. So let's calculate. So if let's start with this structure, we're in the carbon, hydrogen is in the terminal carbon. So this is experimental retention time. So the first peak is 7.87, second peak is 8.21. So let's calculate against the first peak first. So calculated retention time for this is 8.24. So percent error mo against first peak is 4.95. Now let's move the hydrogen to this one. So this is another isomer. So, and then the calculated error mo is 9.58. And then moving it to another carbon. So you have here 7.14. And then here you have 11.7. So basically using both approach. So you can basically, the mass spec here can no longer identify where your hydrogen is attached, but the retention time prediction can tell you where it is based on the percent error. Second unknown, the second peak. So this is the most probable structure so far. Again, this is sulfonate. You have the 98 and 82. And then this is an ether, so it probably can fragment here. So if that fragmentation happens, and then you lost HF, that will be equivalent to your 246 mass. So, however, pwede naman mag-move yung, pwede rin naman ang oxygen mo ay dito or wherever here. Okay, the mass will still be the same. So let's calculate the possible isomer. So first is this one. So again, second peak tayo. So percent error is 7.83. And then if I move my oxygen from here, so this is here. So I move ko siya dito, then my error is 1.07. And then I move this here, you have error of 5.95. And then this one, 6.90. So based again on mass spec and then retention time prediction, the most probable structure for this is the second one. So using the combination of mass spectrometry and then retention time prediction, we were able to provide the most probable structure of these 5 unknowns. So for the first unknown, we compared 4 isomers, and then at the end, we still give it a 2B classification because we can no longer identify if the OH is attached here or this carbon or this carbon. So at this point, we really need an analytical standard. So for unknown number 2 naman, we compared also 4 isomers. And then this is the most probable structure. So we identified as a 2A and unknown 3. So again, you have 2 peaks at unknown 3. We compared 22 isomers. And then the first peak is this one, and then the second peak will be this one. So we set it at 2B if we can no longer tell if, the example for this one, the hydrogen could be in this carbon or attached to this or attached to this one. And then for 4A, for unknown 4, we have again 2 peaks, and we compare 17 isomers, unknown 5. We have 4 isomers, and then all of these are like, this is the most probable structure based on both mass spectrometry as well as retention time prediction. Next is, I will move to the next project, which is the PFAS removal in water. So this is more of like a startup project. So I collaborated, first is, right now we have 3 technologies commonly considered by water treatment facilities to remove this group of compounds. The first one is use of reverse osmosis. The main problem for this technology, we have a very energy intensive. Besides PFAS, natatanggal din niya yung minerals from drinking water. And then another problem is during the disposal. So basically, we're generating liquid waste stream of, you're concentrating PFAS, and then you're not really removing it. You're just taking it away from water and then move it to the ground or wherever. So you're just basically moving it somewhere. Second technology is use of granular activated carbon. So main problem is not specific to PFAS. So other organic compounds can also adsorb to this, and it's not really efficient for short chain PFAS. Again, the problem is disposal. So usually we do landfilling, or you regenerate it using very high temperature, which is very expensive. Next is ion exchange resin. So the problem naman, hindi din siya selective. And then, although yung mga new varieties naman yan ay PFAS specific na, but it's very, very expensive. And then again, the problem is disposal. You do landfill, or you can regenerate with chemical flush, which is another environmental problem. So for this project, we collaborated with Cook Lab. So this, sa UBIN din sila. And basically, we started this collaboration because Cressa is also Filipino. She is a very good friend of mine. So basically, nasa ibang lab lang siya. So we kind of talk, what if I'll try your compounds, to use your compounds to my environmental contaminant. So their group are synthesizing metal organic polyhedra. The main advantage of these MOPs, they are modular, they can be tuned and have permanent porosity. So we're thinking maybe we can capture PFAS in water, and then after we capture the PFAS in water, pwede natin siyang ma-degrade using photodegradation. So the first step for this project is to screen the different MOPs that they synthesize in their lab. So basically, we nag-compare kami ng iron MOPs, copper, and then palladium. And then I think we compared other things, but what we found is iron MOP works. And then the good thing also with iron MOP, so it's very cheap compared to the other metal organic polyhedra that they have. So for this one, so first is the screening. So this shows you, this is already using iron MOP to rescreen other metal organic polyhedras. So this figure shows you, so you have here the control, and then so that means we don't have the iron MOP, it's just basically the water spiked with your PFAS. And then this is ammonium sulfate, and then you have the iron MOP. And then these are the different PFAS that we tried. So these are the carboxylic acid. As you can see, the short chain PFAS are retained in the solution. That means it's not being captured, but the long chain PFAS, we capture it. It's removed, like is starting from PF. So Na is nonanoic acid. So this is C9 to C11. We totally remove it from the water. And then for the sulfonates, it starts with PFOS. And then spores, these are the other groups. So, and then we tried to do characterization of the iron map, and then how it actually, if it's actually binding to the PFAS. So upon characterization, we found out that the short chain PFAS can actually go inside the cavity of your iron map, and then the long chain PFAS are just absorbing at the here outside your map. So this is a very recent project. So, and then both of us graduated, but then right now they are working on it. So what they are doing is, because the iron map, they can tune it. So they're increasing the cavity of this map, so that in such a way that they can totally put the PFAS inside. And then once you capture it from the water, you can take it away from, remove it from the water, and then do a photodegradation. What we have there? Sorry, may napindot ako na hindi dapat. So as a summary, so I did not present you this, but first I developed a method for the analysis of PFAS with available primary standards using liquid chromatography, tandem to higher solution mass spectrometry. And then next is I used that method to basically work on the other projects. So the established method was used to determine PFAS in drinking and source water collected from the Philippines and Thailand. So this is actually a pioneer study, PFAS study specifically in the Philippine water and in Konkan. So there are some studies but in Thailand, but focus on only in Bangkok. And then based on this work, we were able to determine that the PFAS contamination of drinking water is basically linked to its source. So even though meron tayong drinking water treatments, hindi pa rin siya totally na-remove. And then at least 4 PFAS were detected in all commercial bottled water that we analyzed. Unfortunately, I specifically analyze yung bottled water na binibigay for babies, but still PFAS are still there. And then PFAS levels of drinking water samples, although it did not exceed the health advisory for PFAS and PFOA, but still I think it is the monitoring of PFAS in drinking water is really needed. And then second one, so we use an approach combining the experimental retention time, the fragmentation pattern, and then the calculated log KOW to facilitate a structural elucidation of emerging PFAS without available primary standard. And then lastly, we also did to screen self-assembled cages for PFAS removal and to understand the interaction of PFAS with iron map. And that's all. Thank you, everyone.
Thank you so much, Dr. Grace, for this very informative presentation. So, pahinga muna ikaw for a few minutes, inom ng water. Okay. We'll have some announcements, and if I may share my screen as well. So, paki-stop na lang muna yung sharing. So, there you go. Thank you. Ayan. So, habang nagpapahinga ng konti ng boses si Dr. Grace, I will share some announcement with everyone. So today, after this talk around 1 p.m. po, we actually have another web event. It's SciTalk, which is actually it's like a web online talk show by our interns. So today po, it's episode 10 na po, and they have a special episode called FSH Interns Kulitan. So ayan, magkakaroon sila ng discussion on siguro random things. So if you can po, please join us and invite especially your students to this very fun web event on Facebook Live. So kita-kits po tayo dyan. And then, so just like what Dr. Jeff said, we have a break due to the holiday season. So from December 18 to January 8, wala po tayong webinar every Saturday. So we will miss everyone. And then on the 15th, imagine that po, no, 2022 na, ilang araw na lang. We will start off the year with the final lecture. So with DLSU Central Instrumentation Facility on Modern Analytical Methods. And that will be the webinar on liquid chromatography, instrumentation, and applications in natural products research, which will be delivered by our one of our FSH members, Dr. Ana Karen Lacerna. So that's January 15, 2022. So ayan, after nyo pong magpahinga, January 15 po ulit yung balik ng ating webinar sa Sabado. And then we just wanted to emphasize po, no, towards the end, we will be giving some freebies towards the end of the webinar. So I believe our Mr. Marty Mateo shared the link for the raffle giveaway. So on the chat box sa Zoom and also sa YouTube live chat box. So feel free to register there so that way you could participate in the raffle towards the end. So ayan po. And now we will proceed to the question and answer. And actually this morning we're also graced by one of our FSH board member, Dr. Connie Gibas, dialing in from San Antonio, Texas. So we will be facilitating the question and answer. So Dr. Grace, nakapahinga ka ba?
Okay naman.
Okay. So we will spend probably, I don't know, maybe 20 minutes for question and answer. And just so you know, we have a highly engaged audience, both on Zoom and YouTube. So maraming tanong. Hopefully, ma-accommodate lahat. I don't think we can kasi sobrang dami. So, ayan, is Dr. Connie still here? Mama Connie?
I'm here.
Okay, all right. Okay, so I'll start the first question. So the very first question is from Diane Carla Cruz, who's a Zoom participant. So dalawa yung tanong niya. Sabi niya, are all PFOS and PFO hazardous, and are PFAS only toxic when ingested?
Ay, okay. Hindi na pala ako nakamute. Yes, they are hazardous, and I would say it also has like issues when you have it in your skin. So it's not just through ingestion. So once it's in your skin, it starts basically to react with everything. So.
Oh, okay. So is that also at the same level?
Although again, the toxicity depends on the concentration.
Ayun.
So hindi naman yung galing mo sa drinking water, hindi pa yung toxic.
Oh, okay.
If you are like for me working in the lab, like I was dealing really concentrated, then yes.
Oh, okay. So siguro yun yung tanong niya, no? So anong level ba yung considered na toxic? Is there a certain level set by a regulatory agency?
So the EPA, they said 70 nanograms per liter. Yun yung health advisory nila. That means if your level in the water is below 70 and below, like you can still use that water, like lifetime health advisory, you're still safe. But if your level is way, way above that, then that's a problem. And
Ayun, okay. All right. So move on tayo sa next question, Dr. Connie.
Yes. Okay, this is a question from Aileen Beroya. So, Dr. Grace, what are the symptoms of PFAS toxicity to humans? And what kind of first aid or what first aid do you use when you have symptoms like that?
I can't really tell that, it gives you like a specific symptom. So it when you are contaminated with PFAS, if you're already having like issues with your endocrine system, if you're having cancer, that's basically the thing. You cannot tell like, oh, I have PFAS. I don't know.
Oh, so you
Yeah.
mean that it's not an acute condition?
Yeah, it's not an acute. Yep.
Okay. There you go, Aileen.
Okay, ayan. So moving on. Also from Diane, that Carla Cruz, sabi niya, having PFAS phased out, what did they replace it with? So is it really phased out completely, or?
So I discussed earlier, phase out lang yung long chain PFAS, specifically PFOS and PFOA kasi sila yung well-studied. Again, these are very, very useful compounds. So they replace it with what we call emerging. So long chain, they replace it with short chain, thinking that short chain is not toxic, but eventually they figure out, well, short chain is also toxic. And then they kind of twist the structure. So instead of totally fluorinated, they like put like oxygens, they have like ethers, in between, thinking that it will degrade in the environment. But apparently these ether groups, it will break the environment and it will be like a short chain PFAS, which is also toxic.
Ayan, there you go, Miss Diane. So, yeah, we're moving along quite quick. So baka makover nga natin lahat. Thank you, Dr. Grace.
They're very interesting questions, though.
Yes. Okay, so Mama Connie.
Okay, this question from Cliff Moises Florentino. So other than the negative effects, has research also shown, if any, benefits from PFAS?
Health-wise, no. But benefits, yes, it's very, very useful compounds. As you can see, benefits is in the manufacturing process. It's used basically everywhere. That's the benefit. It's a very useful compound. But then environmentally, it's not.
Okay.
So, so you think it's something that we really, manufacturers, especially in the modern world, cannot avoid?
So right now, actually, if you would like Google it, try to Google. This is a bad thing. Try to Google. They have a lot of like issues with EPA. Try to Google DuPont.
So, Dr. Grace,
Mm-hmm.
what do you think of Teflon cookwares?
That's basically PFAS.
I know, but should we use it? Should we not?
I use we can still use it. However, if you start seeing scratches, don't use it.
Oh no.
Yes, because that means it's already like, yeah, once you have the scratches, don't use it anymore.
Hindi na pwede, ayan, to avoid.
Nagre-release na yung PFAS siya, nagre-release na yung Teflon. So it will go to your food basically, and you're taking it. Yeah.
Ayan.
Wow.
Okay, so let's take note of that.
Right now, if you would like buy like Teflon, non-stick cookwares, they tell you already PFOS and PFOA free, right? They kind of advertise that. However, they probably are using different PFAS.
So there was one cookware I used, and their selling point was that this is a PFAS, but it has steel integrated in it. So they said that it's very durable. It doesn't leach out into the food. So is that true?
I can't tell you that it's like totally true, but could probably, as long as you know you don't use it like that long. Once you started scratching things, then that will leach out.
Oh, okay.
Okay.
There you go, Cliff.
Okay, so from Jason Alcano, who is also our PhilSci-Hub intern. And also, hello, Dr. Grace. Such an interesting topic. Actually, I was introduced to PFAS by Dr. Aga in a past seminar. From there, I got interested in the topic. So the first question is there a way to detect PFAS without using sophisticated mass spec methods, like say in situ kits? So, mga strips, ganyan.
They have it actually, but then it's not accurate.
Ayun.
Not really accurate.
Oo. So parang, anong klaseng kit siya, Dr. Grace?
I think I went to like a seminar before. They're using like just to test. So mag-change ata. Parang yung pang pH ganon. So parang hindi talaga siya accurate at all.
Oh, anong levels? Anong ppm?
But again, the levels will be like ppm levels. You cannot detect like
PPB. Okay.
Qualitative lang.
Very qualitative, and then probably it's not even 100% sure.
Gotcha.
Okay, so kailangan pa rin talaga ng
analytical, yeah.
More sensitive. Okay.
Yeah.
Okay, is there an existing benign by design synthesis of PFAS or related compounds?
I think yes, there is, but I can't tell you now. Yeah. There's only one process, basically two processes of synthesizing PFAS, but you can try to research it. Yeah.
Okay, so it's a known process.
It's a known process.
Okay,
it's been existing like 1960s.
Yeah. So is this something that say is there, we will not name names, but is there like a company that just synthesize PFAS, or manufacturers actually produce it as a raw material for their okay.
You can watch Netflix. Definitely, you will know there.
Okay.
Okay. That movie?
That movie or the Netflix documentary. You can watch it.
Okay.
Okay. Ayan. So, ang daming tanong ni Jason. This will be the last one. I recently read a paper on Forever Chemical No More, tackling on how it can be solved using supercomputing simulations. May I ask, what are the ways for PFAS degradation available today?
So, for as of now, yun nga, yung sinabi ko earlier. So, first is you capture it and then you degrade it at very high temperature, which is very, very expensive. So far yun pa lang talaga ang nangyayari. Na medyo, ginagawa na siya on a manufacturing level. So, mas madaming quantity, but it's still very expensive. So you capture it using like resin or like reverse osmosis, and then landfill, and then you do high temperature degradation.
Okay.
Yeah, and then marami namang research available, but then hindi pa talaga commercially na ginagawa. So more on like lab research pa lang, or pilot studies.
I see. Okay. All right. Thank you. Ayan, nasagot mo na to. Teflon classified as PFAS. Okay. Sagot na yan. Okay. So, Dr. Connie.
Okay, from Cliff again. Out of curiosity, would there be a simple process in detecting PFAS or removing it in our water supply? Dr. Grace?
A simple process for detecting wala pa talaga. So kailangan mo din talaga ng kasi in our water supply, so mas mababa pa yung levels niyan. So kailangan mo pa rin talaga ng medyo sophisticated na instruments.
Okay.
But removing it in water supply, yes, the filters work. Yung mga filter na available, magagamit, pero do not use it more than like 3 months, okay? When it has to be
What kind of
replace it.
filters?
Yeah.
What
Like,
kind of filters are they?
it's mostly ano ba yung mga available na yung mga available lang na filters like sample sa Walmart. So for drinking water, you can use it. But again, it can only filter the long chain but not the short chain PFAS.
Okay.
Okay.
No.
I think this was already answered. So from YouTube naman from Miss Manolita White, I guess she's asking what kind of cancers PFAS chemicals have been linked to. So is it mostly endocrine?
Yeah, mga endocrine disruption.
Endocrine disruption. Okay. Okay. Yun nga, it's through the heart. Okay. So siguro let's take a couple more questions and then we can move on to the the highlight of the morning. So nasagot na rin yan, ano? Let's see. Okay, ito, sige, Dr. Connie.
Okay, from Reniel Salgo, considering the levels in water sources now are not exceeding the EPA standards, is it predicted to reach and go beyond such limits? How long will it take?
It can go beyond that limit, especially if we don't remediate it now, especially if we continue to use consumer products that contains, PFAS, that are using PFAS. So as I mentioned earlier, the EPA here in the US, they're not just looking PFAS in drinking water. Now they're looking PFAS in waste, in other waste, basically in soil and some other things. So they're more on doing a holistic research, how to remediate it. So if we can do that, then yes, we can kind of reduce the levels that we have right now. Also, a lot of research are doing more of like finding alternatives to PFAS. Instead of using PFAS in the example consumer products, we're trying to find alternatives, other chemicals that are not as harmful as PFAS. So there are a lot of research working on this, but I think if the big companies will continue to produce it and pollute the environment, then yep. So a lot of work I think has to be done with the regulation.
Right.
Well, yep.
Okay, there you go, Reniel. I have a question, Dr. Grace. So, so for PFAS, you said what are the common things that we use at home aside from Teflon, skillets, or what have you?
So, yung mga let's say pizza boxes, usually coated yan ng PFAS, and then basically yung mga sa food packaging.
Okay.
Are usually coated with PFAS. Yung microwavable popcorn bag, so when you just put like the bag in the microwave and then it'll pop out, you're basically releasing PFAS from that bag.
So yung mga wax paper, is
Yeah,
that?
yes.
Not wax paper, but the other one, parchment paper?
A parchment paper, it doesn't have that, but yeah.
So wala bang FDA regulations on that? Yung mga packaging packaging requirements.
The thing is, I think in Europe they started regulating that, but in the US not yet. Also another thing that I remember is use dental floss. They have PFAS already, especially those that are very, very ano ba yun? Yung masyadong shiny.
Kasi may coating.
Oh.
So, magbalik tayo sa toothpick.
Yeah. I
Ayun.
think there's also yun mga makeup na-detect na rin
No.
sila makeup. Yep. There are some regulations specifically I think in Europe but in the US not yet. So US more on detection pa lang sila. So development of like the libraries and then what level. So but it's tackled already in the EPA but still the process will take long.
But decades have been gone, and we have been using PFAS forever.
Yep.
So I guess the damage has been done.
Yeah, exactly. Yep.
So we are just now starting to get noticing.
Mm-hmm.
Ayan, ito naman from Mr. Marlo Fabia. I think this will be our second to the last question. So are there existing Philippine regulations for PFAS control and management applicable to consumer products and environmental compliance requirements?
The answer is no. Yeah. Honestly, when I was collecting samples there, we don't have it. I mean, even the DNR is not like still aware of it. So
Oh gosh.
Ayun.
we're
Ayan.
very, very behind.
Yeah, so may nagtanong din actually from YouTube kung kamusta daw ba yung awareness about PFAS sa Philippines. So, I see.
Mm-hmm. We're
So,
very behind.
okay, but so kahit research wala sa Pilipinas.
Imagine yung PFAS paper ko, yun yung first research ng PFAS sa Philippines.
Well, there you go, students. This is a good project.
That was published last year. And PFAS was already been in the environment like what, 1980s, 1970s? Yeah. Mm-hmm. Although one good thing, we don't have manufacturing facility of PFAS in the Philippines, but again, now we have a lot of factories using it. So, there's another publication that was recently published about cancer patients. I think they collected samples from a cancer patient from PGH. So yeah, they also analyzed PFAS in the blood. It was, I think, published this year lang. So maybe they want to read that paper.
Okay.
Yeah.
Ayan. It's a good question.
Yeah.
Ayan, yan yung question kanina. Ayan, na-discuss mo na yan. Okay, Dr. Connie.
Okay, from
This is our
Ryan.
last question, yes.
From Ryan Wang, do PFAS bioaccumulate?
Yes, because it's not, it doesn't degrade. So basically it bioaccumulate in the food chain. So fish will get it, we eat the fish, so we will get it, or, based on the food chain. It's just bioaccumulating.
Oh, okay. Ayan. So,
excreted in our body though? Does it get excreted in our body, or what do you call that? I mean, go through the body waste, or is it
some research show that it can be excreted through a urine, but only the short chain PFAS, but not the long chain. The long chain will basically stay in our body.
No, that's really scary.
I mean, there's a research now, 99% of Americans have it. So I think because the research is done in the US, so based on the sample size from the US, but if you would analyze other people from other countries, probably we will also detect it. Just the level is maybe not yet alarming, but we have it in our blood.
Wow.
Forever chemical nga, di ba?
Forever chemical.
Ito yung my forever talaga.
My forever. So basically just transport.
My forever.
From one place to another place. It has, it's soluble in water, so it transports.
So this is a really good field to study for our future aspiring scientists. So we really have a highly engaged audience, and thank you so much everyone for your questions. But because of our limited time, hindi po natin ma-accommodate lahat. But Dr. Grace, what's the best? Is it okay to reach out to you if they have questions? What's the best way to reach you out?
Sa email na lang. Here's
Okay.
my email.
Sige. So, pakitype na lang siguro sa ating chat box, and we will also share that with our YouTube participants. So, ayan. So again, thank you so much sa ating mga nagtanong. And before we proceed to the raffle, alam ko medyo dinedelay na natin. But I would like to present the certificate of appreciation to Dr. Mary Grace Guardian for delivering the webinar, What's in Your Water? Introduction to Per and Polyfluoroalkyl Substances, organized by the Filipino Science Hub and held via Zoom and YouTube Live on the 11th day of December 2021. Given this 11th day of December 2021, signed by our CEO and founder, Dr. Jeff Bunkin, and our Vice President, Dr. JP Onya. So, Dr. Grace, we learned a lot from you. So thank you so much for your time, for sharing your knowledge and your expertise to the PhilSci Hub community. So, sa uulitin. Thank you. Super thank you. So, for the raffle, we are graced by Mr. Marty Mateo, so he will facilitate that. So, Mr. Marty, are you still on? Are you still there?
Yes.
Ayan.
Yes. Hello. Good morning.
Good morning.
Good morning, Dr. Grace. So thank you for your insightful talk. We are reminded to change our Teflon because marami tayong lulutuin. So baka kailangan na nating palitan ng ating mga Teflon cookwares. So thank you.
At La Cruzette.
Yes, thank you for reminding us to change our Teflon wares. Ayan. So we will be proceeding with the raffle. I will share my screen.
Okay.
Pasabi na lang po kung nakikita na po ang ating ruleta.
Ayan, kita na namin. So, ang first prize ay yung Organic Chemistry Model Kit.
Alright, so yan po. Unang prize daw po ay ang Organic Chemistry Model Kit. Let me see. Okay, so bulahin na pa. I-roll na po natin ang ruleta. Alright, so ayan. So ang winner po ng Organic Chemistry Model Kit ay si Rika May Masangkay. For Rika May Masangkay, if you're still watching Zoom, pwede po kayong pumunta sa Facebook page namin and you can contact us through our Facebook page para po maklaim yung prize. So again, for the Organic Chemistry Model Kit, ang nanalo po ay si Rika May Masangkay. Okay, anong next prize natin, Ma'am Dindy?
Ang ring light. Ayan. Na may extendable tripod.
Aha. So ayan, so perfect po to sa mga students na nag-online class and pwede na rin sa mga teachers na nagtuturo. So let's roll the ruleta. Ayan, sino kaya ang mananalo? So for the ring light, ang nanalo po ay si Mr. Alfredo Siga Jr. So Sir Alfredo, if you're still online, you can chat us through our Facebook page to claim your prize po. So again, ang winners po natin for the Organic Chemistry Model Kit, si Rika May Masangkay, and for the ring light with extendable tripod, ayan po, si Mr. Alfredo Ga Jr. Ayan. So back to you, Ma'am Dindy.
Thank you so much, Marty, for facilitating that. So that ends our webinar for this morning. So pinost ko lang po yung ating evaluation link. And so, ayan, nasa chat box na siya. And again, ito po yung ating huling webinar for the year. So we will miss everyone, but we wish everyone have happy Merry Christmas, have a Merry Christmas and a Happy New Year. So super thank you po sa patuloy niyo pagsuporta sa ating platform. And we are excited. We're looking forward to 2022. We have more exciting things for you. So muli po, kita-kits po next year. And Dr. Grace, thank you so much. Dr. Connie, thank you so much for both of your time tonight or this morning. And Marty. So, ayan.
Thank you.
Meron pa ba? Thank you so much. So we'll see you again. Have a good day.
Merry Christmas, Happy New Year.
Bye-bye. Dr. Grace, debrief tayo pala. I'll send the Zoom link just for 5 minutes.
Okay, bye.
Okay.
All right.
I can't leave yet.
Thank you, Dr. Gray.
Thank you. I will
Thank
send the Zoom link. Okay. Thank you.